nanohub.org.
So the point of today's lecture is to basically discuss this syllabus, try to answer any questions you have, and then to give an start to give introductory lectures on these various topics. This is the second year the course has been offered. Last year we had about 15 students enrolled in the course. This year we have 9. Okay. I think this year it'll be better than last year because last year we were feeling our way. We've redone the syllabus, try to make it a little bit more focused. As you probably, if you looked at the syllabus, right, the way the course is constructed is there's about 27, 28 lectures. I give about half of them, and then Professor Rahman gives the other half. The parts I've been assigned to teach are the scanning tunneling microscope section of the course, which is up front. It's basically the first scanning probe microscope. So I think to understand what follows, you got to understand a little bit about STMs. And then I come back at the end of the semester, give about 3 or 4 lectures. Professor Rahman is an expert in vibrational analysis, and he'll talk about, he'll take over the middle part of the course, which will be much easier, I think, for mechanical engineers to understand because that's what you folks do, vibrations, right? So that's roughly how the course is split, okay? So I discussed the course syllabus. The other issue is the mathematics involved in this class, right? And I thought about this based on last semester's experience, right? And it occurs to me there's like four different levels of mathematics that will be used in the course, right? First level you're probably most comfortable with. It's a functional mathematics. It's just formulas where you plug in variables and you can calculate quantities. This is the sort of mathematics that we teach in the introductory physics courses here at Purdue, for instance. That misses an awful lot of detail, right? Whenever you're dealing with dynamical systems, you have to do differential equations. So if you want to appreciate the dynamics of an AFM, you're going to have to deal with a differential equation. So that's the second type of mathematics that we're going to deal with. The third type is this probabilistic mathematics, right? Probabilistic models of electrons or atoms. We're not going to deal with that so much. There's a couple of concepts that we'll introduce that involve concepts from statistical physics, but not a whole lot. And then the fourth level is the fields, the mathematics of fields, right? Unfortunately, charges produce electric fields. Electric fields are vectors, and these vectors propagate through space. And if you're unfamiliar with vector operations, you know, you'll have trouble with that part of trouble appreciating that part of the course. So the bottom line is there's about 3 levels of math that we're going to deal with. The one that we won't deal with very much is the probabilistic models. Those are very useful for simulations. And I don't think we'll use much of that. So that's a warning up front, right? The other issue is measurements, the units that we use in this class. To the best of our ability, we're going to try to follow this MKS units of measure. This is the meters, kilograms, seconds. Forces are measured in newtons, right? We're going to try to follow that system of units religiously. Okay, there'll clearly be exceptions. I can tell you one exception up front is this concept of an electron volt, right? Electron volt is a very convenient unit of measurement, right? You should understand what an electron volt is, and you should understand how it's related to a joule, right? We'll try to make it clear in lecture, but that is one case where we'll flip back and forth between joules and electron volts, right? A joule is hard to, small joules, 10 to the minus 19 joules is hard to comprehend. But 1 electron volt is much easier to understand, right? So you'll see that conversion back and forth throughout the semester. The other thing I find useful, I try to tell students whenever they take a course, it seems obvious, but you ought to buy a note card. And you ought to start writing down constants or formulas or concepts on that note card that are important as the course progresses, right? So rather than spend your time scurrying, looking up constants in the back of a book somewhere, right? This is a copy of my note card. I got this on my desk at home, right? So these constants I use a couple times, 3 or 4 times a week, right? After a while, you can memorize them, right? There will be similar concepts associated with AFM formulas and AFM concepts that will be derived. So why not start a separate note card for that, okay? If you do that religiously through the whole semester, at the end of the semester, I guarantee you will have something that you can take with you in your future studies of AFM, right? So I just, you know, it's kind of obvious. Probably most of you do that anyway, but just make a case of it. And then the other issue is how to get most from the course. I think it's fair to ask this, to go through this, right, up front, just to tell you what you should be looking for, right? I think you should come to class and take careful notes, right? I think you should really carefully listen to the vocabulary because the words are important. Some of the words that you use mean different things to different people, right? Mean different things to different disciplines. So you really have to focus on that. One of my themes as I get older is to tell students do not become passive consumers of information, right? What I've noticed, at least when I teach physics courses, is that students just sit there and I just explain things to them. No questions asked. It's just like watching TV, right? If you do that, you are a passive consumer of information, and that's not part of the education process, right? So it's in your best interest to ask questions, right? To try to get involved in this material. So don't be afraid just to ask, so what? Because I think we can answer the so what questions, but if you don't ask them, you know, you're not going to get any insight into what we're trying to talk about, right? There will be a few oh wow moments during this semester, and you should try to be aware of those moments, right? You're going to be told things that you probably didn't appreciate, or maybe that you're going to look at in a different light, right? So to me, that's what makes this course fun, is to identify a few of those oh wow moments. Hopefully you'll get one oh wow moment every lecture, but that's overly optimistic on my part, right? But if you have a few of them this semester, that's great. The other thing I find to be useful is to tell students to work through these confidence building exercises, right? You got to ask yourself simple questions, and you got to answer those questions, and you got to build up confidence in this material. It's not easy. It's not straightforward. It involves input from many different disciplines, right? And if you don't do these simple little what if type things in your own mind or at home, right, you're not gonna get as much out of the course as possible. So this Veda simulation software will give you all kinds of experience in building confidence, because you can ask simple questions. All the math is done for you, right? You can get output from this Veda simulation that will allow you to build up intuition and understanding. That's important, I think. Please do the homework problems, turn them in on time. I like to encourage students to adopt the attitude, what I can't calculate, I don't really know. I mean, you can write down a formula, but unless you put some numbers into it and run through a calculation, I'm not sure you understand what the formula means, right? So just the exercise of picking numbers to put into various formulas gives you great insight into what's going on, because you got to get the units right, you got to get the order of magnitude correct, these things build confidence, increase your understanding. So I really like to adopt that. I hope you adopt that attitude, right? I don't think you'll fall into the trap about which formula do I plug into, because these problems are complicated enough. There is no one bottom line formula. So this is not like these introductory physics classes where there's a formula that you can draw a yellow box around it and say, this is it, right? So, and then the other thing I can tell you is just read as many books in parallel as you can, many articles, right? So it's a research course in that regard. You gotta, you know, I always tell students, right? You'll never remember, a year from now, you'll never remember the content of any lecture that's given in this course. But if you teach the content of that material to yourself, that will stay with you for a long time, right? The only way to teach that to yourself is you have to go, after the lecture's over, you got to go back and go through it and work it through, internalize it, right?